Here's another conservation of energy problem where we have a girl going down a slide at a park, and her velocity down the slide is 2.5 meters per second. The slide is 10 meters long, and the top end is 4 meters above the bottom end. So we should start off by just drawing a really quick sketch here. So we have the slide, which is 10 meters long. We know that the top end is 4 meters above the bottom. There's your ground. And the mass of the little girl is 30 kilograms, and her final velocity is 2.5 meters per second, and she's starting from rest, so with a velocity of 0. So her gravitational potential energy at the top of the slide, and this is not in any way related to the velocity, so all we need is the height. Now this is your change in height straight up from the ground. So her h is going to be 4 meters, not 10 meters. So what this looks like is her gravitational potential energy, mgh, is equal to her mass, 30 kilograms, times 9.8 newtons per kilogram, times 4 meters, which is the height. This leaves us with 1,176 joules. So that's how much potential energy she has at the top of the slide. Her kinetic energy at the bottom of the slide is simply a function of her velocity. So that means that EK is 1/2 mv squared, 1/2 30 kilograms times 2.5 meters per second squared. That leaves us with 94 joules of energy. How much kinetic energy is lost due to friction? So we have to take a look at this and say that this doesn't make sense because obviously the conservation of mass states that whatever energy she starts with, she has to end with. So there's a lot of energy that's lost here. So the energy lost due to friction, so we could say the E lost, is simply going to be her final energy minus her initial energy. In this case, her final energy is all EK and her initial energy is all EG. So that's 94 joules minus 1,176 joules, which leaves us with 1,082 joules of lost energy. Lastly, we want to know what is the force of friction acting on her as she goes down the slide. So it's important here to remember our work equation, which is work equal to the force, in this case the frictional force, times the change in displacement. So we know the work done by friction. The work done by friction is going to be equal to the amount of energy lost due to friction. So those values are going to be the same. We can rearrange our equation then to say that the force of friction is equal to the work divided by the change in displacement. That's 1,082 negative, since it's energy lost, divided by 10 meters. That's the total distance she goes down the slide because, again, work, energy, friction all have to be in the same direction. So that leaves us with negative 108.2 newtons. And if you account for significant figures, you're probably in the range of negative 100 newtons of frictional force.